Hi everyone. So thank you for clicking on our tutorial video. My name is Sarah, and along with my group mates Paige, T, and Melanie, we're actually going to present on a convective heat transfer over a flat plate problem. So this is our table of contents that you can refer to later on. But we'll introduce ourselves first. So like I said earlier, my name is Sarah, and I'm a third-year chemical engineering major with entrepreneurship as my minor and core as my concentration for my major. Right now, I've been working on my ukulele skills and have just really been practicing a lot of Taylor Swift songs on it.
Hi, my name is Paige. I'm a chemical engineering major, third year, and my concentration is core. And I've mostly just been like watching TV and playing Animal Crossing.
Hi everyone, my name is T. I'm also a third year chemical engineering major with a minor in bioinformatics. I love watching cooking TV shows, eating good food, going on random adventure to take pictures. I also love to go skiing whenever I have time.
Hi everyone, I'm Melanie. I'm also a third year chemie with a biomedical concentration, and in my free time I love listening to music and learning some stuff about different languages.
Now that we introduced ourselves, we're going to go over the motivations for understanding this problem and also the applications. So our problem that you'll see later on is actually based on the convective heat transfer that occurs in tissue engineering, which is a division of biomedical engineering that aims to restore and improve different types of tissues. Tissue engineering is important as of recent because it actually allows us to decrease the occurrences of organ failure as well as major tissue damage on the operating table. Um, this means that we can increase the rate of transplants of some organs like the heart that are really hard to find in good condition. In the problem our group chose, a cell mass is being held on a scaffold. So to clarify, tissue scaffolds are structures that support cell growth and mimic three-dimensional structures of extracellular matrices to create a graft that can be implanted in vivo. Scaffolds are important in tissue engineering as it provides a platform that allows a lot of important medical issues to be solved. The scaffold's heat transfer characteristics matter because they could change its effectiveness in providing a platform for change in the biomedical industry. One important aspect of scaffolds is actually its pore structure, which, as I mentioned earlier, facilitates cell growth and affects the quality of the grafts the scaffolds help produce. Pore architecture was found to depend on heat transfer by Dr. Guo from the University of Alabama in order to form these alginate scaffolds. The side and top cross sections demonstrate a pore alignment parallel to the heat transfer directions, which means that heat transfer, is at least partly responsible for developing the overall architecture for each region. The side cross section is kind of irrelevant because it's only affected by conductive heat transfer. But on the other hand, the top cross-section area was actually shown to have a slower heat transfer because heat needs to travel a greater distance through not only the glass from the petri dish, but also trapped stagnant air that is in contact with the upper surface of the sample. This shows that convective heat transfer plays a part in manufacturing the scaffold and therefore should be an important factor to discuss when creating the scaffolds.
Looking into more everyday applications, the human body is a good example of where convective heat transfer over a flat plate is apparent. One example of an application can be heat transfer to the skin, which when looking at a segment can be treated as a flat plate. The surrounding air is not completely static and has some fluid flow velocity, especially if it is a windy day. Another type of a surrounding fluid can be water when an individual is swimming in a pool. All of these are examples of a convective heat transfer as the temperature change on the surface of the skin is affected by flowing fluid around it, and the temperature of the surface is affected by the flow rate or velocity of that fluid. Another example is the lungs, as when there's inhalation during the process of respiration, there is an intake of air or oxygen, and in this case, the sections of the walls of the lung can be generalized as a flat plate when looking at smaller segments. In a research paper published last year, researchers implemented this idea of heat transfer to a study by having cyclists train in a heat chamber where the ambient temperature is high for 5 days a week for 5 weeks to see the effect that the heat training can have on the hemoglobin mass or count in the blood. For their investigation, it was hypothesized that with an increase in heat in the surrounding environment during exercise, there would be an increase in plasma volume in the blood, and eventually that would lead to an increase in the hemoglobin mass, which helps to better facilitate exercise performance. And their hypothesis was proven to be correct, as there was actually an increase in the hemoglobin mass.
Now we will be going over a little bit of the topic overview, and you can see even more of the topic overview over on our document. So here is kind of an example of a momentum boundary layer, and looking at this momentum boundary layer, we can actually derive some ideas for our thermal boundary layer. So thermal boundary layers are very similar to momentum boundary layers that we've learned in 101A. For thermal boundary layers, the different type of motion drives which type of heat transfer will dominate in each region. So for example, in the laminar region, viscous forces cause conduction to dominate. And then in the turbulent region, eddies and vortices cause advection to dominate. Therefore, as you move along the plate, your heat transfer coefficient is going to change. So the heat transfer coefficient H is a function of X.
Another analogy to what we learned last quarter would be dimensionless numbers. And thinking about kind of the important terms here, we have the Prandtl number, which is the ratio of momentum to thermal diffusivity. And just to remind you all, the momentum diffusivity tells us how well momentum is transferring through the system. Because for more viscous materials, you're gonna see a thicker boundary layer relative to something that is less viscous. For our thermal boundary layer, our kind of equivalent terms for that is thermal diffusivity, which tells us how efficient the system can conduct heat out of the plate and into the fluid. The significance of the Prandtl number is that it tells us how fast thermal diffusion takes place compared to momentum diffusion. Another important dimensionless number that we're going to look at is the Nusselt number, which effectively is how convective a fluid is versus its conductivity. The significance of the Nusselt number is that it shows how much heat is transferred by convections relative to the heat transferred by conductions. When we have a Nusselt number closer to 1, our fluid transport is purely driven by conductions, and a Nusselt number in the range of 1 to 10 signify that we're in the laminar regime, and larger than 100 indicates that there is active convections and we are in turbulent regime.
As explained earlier, the heat transfer coefficient will change as a function of X. How it changes as a function of X, however, depends on the regime that it is in. Here are the functions for the heat transfer coefficient for the laminar and turbulent regimes. And then we have even more equations for the laminar and turbulent regimes in the document. Since the heat transfer coefficient changes as you move along the plate, we need to be able to find some sort of average heat transfer coefficient. This is the basic integral needed to find the average heat transfer coefficient, and we'll go into more detail on how to solve this in the document. And now we will go over our example problem, which includes the 7-step method and our assumptions.
So for the example problem, we have chosen 19.14 from our textbook by Welty. And the problem reads, an engineered tissue system consists of a flat plate of cell mass immobilized on a scaffold measuring 5 centimeters in length and is 0.5 centimeters thick. The bottom face of the scaffold is exposed to water and organic nutrients. The top face is exposed to flowing O2 gas to provide O2 for aerobic respiration. At present, the specific oxygen consumption of the tissue mass is 0.5 millimoles of O2 per centimeters cubed cells per hour, and from respiration energetics, the energy released by respiration is 468 joules per millimole of O2 consumed. We are interested in using the flowing O2 gas at 1 atm to control the temperature at the surface of the tissue scaffold. The properties of O2 gas at 300 Kelvin are the density being 1.3 kilograms per meter cubed, the specific heat capacity being 920 joules per kilogram Kelvin, the viscosity being 2.06 times 10 to the negative 5 kilograms per meter second, and the thermal conductivity being 0.027 watts per meter Kelvin. We are interested in determining the O2 flow rate necessary to keep the surface temperature within 10 degrees Celsius of the flowing gas temperature. This means that the surface temperature has to be below 310 Kelvin or 37 degrees Celsius. The parts, a quick overview of what the parts are for this problem is we would have to solve for the Prandtl number, the heat transfer coefficient, the Nusselt number, the average or mean heat transfer coefficient, and the required values for the Reynolds number and the fluid velocity.
So to solve this problem, we are gonna go through the 7-step methods. The first one is basically just defining the question. It is important to know what the questions is giving us. So here we are given a flat plate with a length of 5 centimeters and a thickness of 0.5 centimeter. The top face of the plate is exposed to flowing oxygen gas. The bottom face is exposed to water and organic nutrients. The property of oxygen gas at 1 atmosphere and 300 Kelvin or rho equals to 1.3. Heat capacity is 920. Mil is 2.06 times 10 to the negative fifth, and K is 0.027. The questions are asking us to find A, the Prandtl number, B, the required heat transfer coefficients, C, the Nusselt number, and D, the equations for the mean heat transfer coefficients, and E, Reynolds number and the fluid velocity.
Here we have a diagram drawn out for this problem. We have our scaffold with length L and thickness T as the flat plate, the water and organic nutrients below the scaffold, and the O2 gas above the scaffold. Note that since we are looking for the surface temperature on the side that is exposed to the oxygen gas, it is safe to assume that the water side has negligible effect in the heat transfer. We also have the O2 consumption and energy released, or the standard enthalpy of reaction of O2, illustrated on the scaffold going in opposite directions. As with oxygen being consumed, we have a release in energy. All the properties and values needed are listed on the right.
Some of the assumptions that we are making to solve this problem is that our fluid is Newtonian and incompressible. The system is in steady state, which means that all state variables are constant with regards to time. We have constant energy generation rate terms, no thermal contact resistance, no slip, which means that the speed of the flow is 0 at the surface. Our pressure is constant since we have a flat plate. Laminar flow starts at the leading edge of the plate. Heat transfer is one-dimensional in the y directions, and we neglect radiation heat transfer, and the critical Reynolds number is 2 times 10 to the fifth. So this is our fourth and fifth step of our 7-step method, which is strategy and solving. For A, the question is asking us to find the Prandtl number for the flowing fluid. Our strategy to solve this problem is to express the Prandtl number and then just substitute in the corresponding variables and solve for PR. Here we have PR equals to nu over alpha, which equals to mole times the heat capacity over the thermal conductivities. Substitute in all the values for the variables. We got Prandtl numbers of 0.702, which is less than 1. This tells us that the thermal diffusions take place faster than the momentum diffusions, and that the thermal boundary layer is relatively thicker than the momentum boundary layer.
Moving on to part B, the question reads, based on the process energy balance and heat transfer, what is the required heat transfer coefficient H? To start off, we first have to do an energy balance on the control volume, which is the scaffold. Applying the assumptions and information given, we know that there is the rate of energy generation and rate of energy coming in, which are from the heat generation from respiration and from convection. From this, we get an equation that is in the form of Newton's law of cooling. So we have the heat transfer rate per area equals H times the difference between the surface temperature and the ambient temperature. In order to alter this to a form that is more appropriate for this problem, we will rewrite it using the proper equivalencies to go from solving for the heat transfer rate per area to heat transfer rate per volume, or Q dot. Rearranging the equation so that we solve for the heat transfer coefficient, we end up with H equals Q dot times the thickness T divided by that difference in temperature from between the surface temperature and the ambient temperature. Next, we have to get the value for Q dot, and that is using the values given from respiration. We have to multiply the oxygen consumption to the energy released, and then convert from hours to seconds, and we have a Q dot is equal to 0.065 watts per centimeters cubed. The final step is to plug in all of these values in the rearranged equation for H, and you end up with a heat transfer coefficient of 32.5 watts per meter squared Kelvin.
in C, the question is asking us to find the Nusselt number. Our strategy for solving this problem is to express the Nusselt number, substituting the given values for the corresponding variables and the H value calculated from part B. So the Nusselt number is equals to the convection heat transfer coefficients times the length of the plate over the thermal conductivity. Replace all the given values. We got a Nusselt number of 60.2. This is the average Nusselt number over the entire plate, and this is one of the trouble spots that we have that we will go over later in the slide.
Part D asks for the mean heat transfer coefficient, which is an integral average value obtained by integrating the local values hx from x equals 0 to x equals L. If the O2 flow is assumed to be laminar, what is the needed convective heat transfer correlation? So the strategy to find the average heat transfer coefficient is, one, we need to determine which h functions to use based on the regime and put it in terms of x. So you need to be able to determine if the flow is only laminar or if it is also turbulent. And then two, we need to integrate to solve for the mean heat transfer coefficient, h bar, using the equation shown. Note that we have a trouble spot, so we will be clarifying any confusion on the difference between the heat transfer coefficient h and the average heat transfer coefficient h bar on slide 36. Now on to solving our example problem. Since we know the flow is strictly laminar, we can just use the laminar equation for the heat transfer coefficient. Then we just need to put it in terms of x by plugging in the Reynolds number. Next, we need to solve for the mean heat transfer coefficient h bar using the integral shown. Finding the bounds for this integral is another trouble spot that we will go over on slide 37. In our case, since the flow is strictly laminar, we can just say it goes from 0 to L. And then after integrating, we find that the average heat transfer coefficient is h bar equals 0.664 K over L times the Reynolds number at L to the 1/2 times the Prandtl number to the 1/3.
Now for the last part of the problem, they're asking for the required values for the Reynolds number and also the fluid velocity V infinite. So for the strategies for this problem are to express the laminar flow of the Nusselt number first using h bar from part D in terms of the Reynolds number for laminar flow and also the Prandtl number. After this, we rearrange this equation to solve for the laminar flow Reynolds number and then substitute the given and previously solved variables into the equation in order to find the numerical value of Reynolds number. So as you can see below, we have the equation of the Nusselt number from the textbook, and then we actually substitute the h bar equation. So this portion of the problem confusing because it's difficult to discern between choosing the h or h bar equation. So this trouble spot will be acknowledged in slide 38, as you can see here. After substituting h bar, we can cancel out some variables to find that the Nusselt number is 0.664 Reynolds number to the 1/2 times Prandtl number to the 1/3. And then as we rearrange the equation, Reynolds number is the square of the Nusselt number over 0.664 Prandtl number to the 1/3. And then after we substitute all of the numerical values in, we get that the Reynolds number for a laminar flow is 10,401. So that was only the first part of the problem, and now we need to solve for the fluid velocity, V infinite. So for this portion, we actually express the Reynolds number first in terms of the equation that we actually got from 101A. And also after this, we arrange the equation to solve for V infinite, and then we substitute the given and previously solved variables into the equation to find V infinite. So as you can see, the Reynolds number equation is for laminar flow. And instead of using the x value that we have in 101A previously, we're using L because the Reynolds number is for a localized area. And after we arrange this equation, we get that V infinite is Reynolds number times the viscosity over density times the length. And then, as I said earlier, we substitute the values that we have to find the V infinite to be 3.3 meters per second.
Now that we're done solving all the parts of the problem, it is time to make sure that all our units match up and that our values are logical. And this is the sixth step of the 7-step method. For part A, the Prandtl number is 0.702, and checking the units, we see that there are none left as they all cancel out, which is correct since the Prandtl number is dimensionless. And our value of 0.702 is logical as it is between the values of 0.6 and 60, which is the range for the laminar assumption, thus holding true. For part B, once again checking the units, we end up with H as watts per meter squared Kelvin. And as for our value of 32.5, it is logical as typically for forced convection of gases, the heat transfer coefficient is between 25 and 250 watts per meter squared Kelvin, and respiration is considered as forced convection as there's an inhalation process, which is being the forcing of air inside, and that is giving us a valid result. For part C, all the units cancel out for the Nusselt number, resulting in it being dimensionless as expected. And the value itself is also once again logical as it is less than 100, indicating that our laminar assumption still holds true.
So for part D, the H-bar equation is as shown below, and after carrying out a unit analysis, we find out that all of the variables give the unit of watts per meter squared times Kelvin, which makes sense because that's what an H-bar unit would be. Now for part E, the Reynolds number is shown to be 10,400-ish, and that value is less than 2 times 10 to the 5, which is the Reynolds number threshold given in the problem. So this makes sense because we've been assuming that the flow has been laminar, and this only just confirms that the flow is laminar. Now to move on to the fluid velocity, the equation is as shown below, and it shows that after carrying out a unit analysis again, all the units cancel out to meters per second. V infinite also has a value of 3.3 meters per second, which makes sense, which is low and makes sense because there's little oxygen needed to maintain the scaffold's temperature around room temperature. Now that we're done with the double checking step, we can move on now to the trouble spots, and then after that, we'll move on to the 7th step, which is the generalization step.
One trouble spot that our group came up with is that since heat transfer coefficients H is changing as a function of positions, we have to be clear about the distinction between the local and the average Nusselt number. So the equation given is the similarity solutions to the Laplace solutions for our Nusselt number. You can see that the local and the average Nusselt number is different by 1/2. Nusselt out averaging out what the local Nusselt number over the entire distance of the plate. This number is helpful in terms of engineering problem type of analysis when we want to look at the average Nusselt number over the entire structure as opposed to knowing exactly what the Nusselt number is at any given positions. And in our problem, it allows us to easily calculate the fluid velocity V infinity over the entire plate using the average Nusselt number as opposed to the local Nusselt number.
Another trouble spot is that H is not equal to H bar. H is the convective heat transfer coefficient and H bar is the average convective heat transfer coefficient. It is important to be aware of this difference, and although the problem statement for this example problem explicitly stated that the average heat transfer coefficient is an integral average value from 0 to L over local H of X values, one can get confused and treat one for the other when they aren't given that information. Another mistake may be using the H value instead of H of X, which is the local value, and the integral for the H bar, which will not provide accurate results. Also note that for H of X, it is important to know which flow regime the problem is dealing with, either laminar or turbulent. Below are the equations for where each type of heat transfer coefficient is used.
When finding the average heat transfer coefficient, it is important to integrate over the whole plate, but you must determine which region is laminar and which region is turbulent. For flows with both laminar and turbulent regions, you must split up the integral to account for the different H terms. XC is the transition point where the flow turns from laminar to turbulent, and it can be found when the Reynolds number is equal to 2 times 10 to the 5th. For our example problem, it states that the flow is all laminar, so XC is just equal to the entire length of the plate. And then since XC is equal to L, our integral can be simplified.
So another trouble spot is actually the Reynolds number that we found in part E. It seems that the Reynolds number is large, which doesn't really make sense when you remember 101A because the threshold is very low for that. But this trouble spot can be eliminated by just considering the fact that the Reynolds number for a laminar flow would be different in a flat plate um, in a flat plate compared to a conduit. So as you can see below, the flat plate maximum Reynolds number would be 2 times 10 to the 5, like in the problem statement, while the conduit maximum Reynolds number would be just 2 times 10 to the 3. This just shows that the value that we got, which is around 1 times 10 to the 4, just makes sense. Now that we're done with trouble spots, we'll move on to the last step of the 7-step method, which is the generalizations.
One generalization is the relationship between Prandtl number and the heat transfer rate. That is, for our given fluid flow problem, the flow conditions remaining the same. If we use fluid that has lower Prandtl number at the same temperature and pressure conditions, for example, we use flow of air or nitrogen instead of oxygen, we will have a higher heat transfer rate.
Here's the general form for the average heat transfer coefficient for flow that is both laminar and turbulent. It is important to note that XC is again the critical X value where it changes from laminar to turbulent. And as talked about before, in our example problem, the flow is only laminar, so XC was equal to L.
So for the generalization of the laminar flow Reynolds number, you can see that it's calculated by getting the square of the laminar Nusselt's number over 0.664 times Prandtl number to the 1/3. And that is actually also equal to the density times V infinite times the length over the fluid viscosity. In addition, the Reynolds number in this case should be less than 2 times 10 to the 5 for it to be valid. And for the last generalization, we can see that a higher flow rate results in a lower surface temperature. This makes sense because the surface of the scaffold starts to reach surrounding temperature faster. And this is shown by the velocity, because the velocity is inversely proportional to the temperature, as you can see on the equation on the right.
Thank you for watching our tutorial, and I hope you got something out of it.